Hello, everyone. My name is Martin Vecev, and I'm a professor of computer science at ETH Zurich. And welcome to the fourth edition of the Reliable and Interpretable Artificial Intelligence course. Now, this year, due to popular demand, we have decided to make the lecture videos public, as well as the lecture slides and the exercise sheets and the solutions. So let me tell you a little bit about myself. I'm originally from Sofia, Bulgaria. I did my undergraduate degree in computer science in Canada, in Simon Fraser, then a PhD at Cambridge University in England, and I worked for several years as a researcher at the IBM TJ Watson Research Center in New York. Following that, I joined ETH Zurich, where I have been a professor leading the SRI lab for the last 8 years, in fact, close to 9 now. Now, beyond academia and beyond academic research, I'm actually quite interested in startups and commercializing some of that research and making it public. So I have actually founded 3 startups together with my other co-founders. One startup is called DeepCode, which focuses on machine learning for code. It builds a machine learning platform for code review. I have also co-founded a startup in the area of security, and recently we have co-founded a startup in the area of this course called Lattice Law. This is in the area of safe artificial intelligence, reliable AI. Okay. So what are we going to do in today's lecture? There are 3 parts that we'll go over. So first, the motivation for the material, why we're studying the concepts that we're studying. Then we'll have a very high level overview of the material, just to give an intuition, the kind of questions that we want to answer, and a little bit of technical preview. And finally, we'll discuss the course organization. So the purpose really is for you to get an idea whether you want to take this course, whether you want to listen in further, or you want to take something else. Okay, so as you know, artificial intelligence, and specifically deep learning, a branch of artificial intelligence, has caused many disruptions, positive disruptions, over the last many years, ranging from autonomous driving, to medical discoveries, to game playing, natural language understanding, fraud prevention, earthquake prediction, and many, many more. Right? You see these kind of announcements in the news all the time. However, there are many, many problems with today's AI systems. And for example, let me give you one example why building modern AI system is actually very difficult. So let's look at this picture on your left. This is a picture of an animal. And I can ask you the following question: what animal do you actually see on the picture? And if we were in a physical lecture room, we would have a few seconds where you could guess that animal. But you have some thoughts probably. And you would classify it as a panda. And a modern AI system based on deep learning can be trained, given many such images, to predict correctly that this is indeed a panda bear. Now, what happens here is that if you take this image, let's call it X on your left, and you add a little bit of noise here in the middle. Let me annotate it here. The pencil. So we add a little bit of noise over here. Okay. And this results in a new image on the right, over in the middle here. Okay. Now, what happens is, if you look at the image here, X, this image X here, and the new image that we created by adding a little bit of noise to X, right, to every pixel in X, is that the new image looks pretty much identical to us humans as the first image. However, a modern AI system, vision system based on deep learning, can mispredict that image, and instead of a panda bear, predict it as a gibbon. Okay, so that's a misprediction that a human is unlikely to make. All right. It's on here. Now, let me give you another example. So here we saw an example of, change to the image that is imperceptible to the human eye, all right, and which can fool the AI system into a misclassification. Let's look at another example here. Now, what can also happen is that the change is not imperceptible. That is you can detect this change. You can see the change. So here we have an example of a stop sign on the left. And what has happened is that an attacker has added some stickers here. These black stickers, white stickers, and so on. I'm underlining here. And if I ask you still here, even though there is a perturbation, visible perturbation to the sign, what sign do you actually see? You would probably still say that you see a stop sign, right? But this can actually fool this AI system based on deep learning into thinking that they see something else. So they can take this stop sign as input, and then what can happen is they can actually misclassify it to a 45-mile-per-hour sign. If the system is installed in a autonomous driving vehicle, it can actually cause the car to crash at some speed. So these kind of attacks were demonstrated in a paper in CVPR a couple of years ago. All right, and there are many more such examples of how you can actually fool these systems in ways that it's difficult to fool humans, even small children. So let's look at another example here. So here we have a three deep neural networks. We have the yellow network over here. Let's look at this picture on our left. We have the green neural network over here, and we have the red neural network over here. So what you see here is that we have a picture. Okay, we have this picture here on the left. This is the picture C1, and two of the networks, the yellow network and the green network, tell the car to turn left. Okay, which makes sense. You don't want to go right here. But because of these black stickers over here that we are scratching now, the red network, then red neural network can get confused and say that it wants to go on the right, which is not where you want to be. All right, let's look at another picture over here in the middle. Let's look at this picture here. Here we have we have some black spots over here that we have on the picture, which still wouldn't fool a human. A human would say, let's go left. But this time, two of the networks, the red network and the yellow network, correctly say, let's go left. But the green network, the third network says, let's go right. This is the C2 network says, let's go right, which is not right, which is not correct, not what we want. Okay, here's another picture, a last one. Again, we have some perturbations to the picture here, some black spots, which again wouldn't fool a human, but they successfully managed this time to fool the yellow network. Okay, so in each of the three pictures, what we have seen is that we're able to fool a different network, okay, to go in the wrong direction. All right. So we just clear the drawings here. So what we see is that there are many different examples for and ways in which we can actually fool these AI systems based on deep learning. All right. And many of these issues that we see and that that are rising today have triggered much action from funding agencies, from companies, from governments. Here is a couple of them, a couple of examples. The EU, the European Union, has issued ethics guidelines for how to build trustworthy AI systems, different guidelines that you can take a look. DARPA, a research agency in the US, has started a new research program called GUARD on, again, building more reliable, more trustworthy AI systems. And there are many more such initiatives towards making AI systems more reliable. Again, different programs, different research programs. And what's interesting here is that, Hinton, who is one of the winners of the Turing Award a few years ago, says, my view is to throw it all away and start again. I don't think it's how the brain works. We clearly don't need all the labeled data. Future depends on some graduate student who is deeply suspicious of everything I have said, suspicious of potentially how deep learning even works. And so to see really what's next here in this entire area of AI, and specifically in the data-driven space, deep learning and models of learning-based models, we need to take a step back and pop up a little bit and see where we are. So one thing we should realize is that traditionally we have had 3 waves of artificial intelligence. So the first wave, and there is a reason why we look at them now, because all of these techniques are going to be useful to us. In the first wave, which is roughly up to the early 2000s, there are many systems that were built based on rules. For instance, translation systems based from one language to another language. Okay, these are based on rules, based on deduction, typically handcrafted. Logic plays a very strong role. And the nice thing about the systems is that they can explain why a decision was taken. Okay, you can really explain this. But the problem is that they do not deal well with the real world. They don't deal well with noise or uncertainty in the input. And so small changes potentially to the input may require many more rules, and the systems get very brittle, get messy, and so on. Now, in the second wave of AI systems, really the systems are based on data and based on learning from data. So the program, if you like, the computation, the function is induced and learned from data, based on some form of search, and optimization. And the nice point here is no human effort is required. Well, partially so. Still, you need to sketch in a way the function and just leave the parameters as something that can be learned from data. The nice point here is that these systems tend to deal well with uncertainty, uncertainty of the real world. The problem is, however, that they have a difficult time explaining their decision. It's hard to ensure that they're safe, they're reliable, very limited logic capabilities. And this is roughly where we are with deep learning today. So now the question is, how would the third wave of AI systems look like? Systems that combine the strengths of both approaches, based strengths of the symbolic approach, of the rule-based approach, with the learning-based, data-driven approach of the second wave systems. Okay, and there's a nice short video by DARPA which goes over a little bit at a high level over these 3 ways that you can take a look. So just to summarize, the first wave of systems is based on symbolic reasoning. Pretty much logic, deduction, abstraction is a very important component there. Compositionality, modularity, topics that you typically learn in logic classes, in analysis classes. The second wave is based on optimization, probability, data, inducing functions from data. Another question is really, how would this third wave AI systems look like that combine both symbolic reasoning and data-driven probabilistic reasoning, right? And one thing to say here is that many of the developments of how these combinations would look like are still in its infancy, still being explored, still being defined. So it's, this area, I believe, is of huge interest, something that we need to be studying, and there is a huge potential here. And the course material, the Reliable AI course that we're teaching now, is an instance of this question. It is one instance of this question. It does not address everything here, but it is just keep that in mind. That is just an instance of this problem, this direction. In our lab, we also explore many other directions at the intersection of symbolic and data-driven probabilistic. For instance, probabilistic programming. We have built a solver which can compute exact distributions of probabilistic programs. We have also worked on and still working in the area of learning from computations, learning from programs, not just learning from data, images or videos, but also from computations like code, functions. And the startup Deep Code is actually an instance of this direction. It's exploring a topic within that space. There are many other intersections. For instance, learning heuristics for different solvers like SMT solvers, theorem provers, optimization, and so on. And trustworthy AI, the whole safe AI space, is again one example of the third wave of AI systems. And the RIAI course, as I mentioned already, covers this space. That's what we'll be looking at here. So what is this course about? What is the RIAI course about? Really, it's a glimpse into the latest AI research. It's the focus of the course is on understanding and mastering the latest advances, okay, in attacking and defending deep neural networks, on proving properties about computations, about AI systems like deep learning systems, on combining logic and neural reasoning, both for querying and for training models, incorporating background knowledge, reducing the amount of training data as well, because it relates to this point, as well as interpreting the behaviors of neural networks specifically. And so, the course is really about, the fundamentals, how many of these concepts work, and how you should be able to apply these concepts for if you are trying to build these more reliable, robust neural networks. Okay. So let's go over a little bit some of the topics that we'll cover. We'll go over this at a very high level. This introductory lecture today is not meant to be very technical. It's just to give you a little bit of a feeling about what are the questions really, and what is interesting here to look at. Okay. So let's start with attacks and defenses on the deep neural networks. The kinds that I already showed you several of earlier in the lecture. So we already looked at some of these, imperceptible perturbations, changes to the input which cause misclassification. Perceptible perturbations which wouldn't fool a human, but can fool the deep neural net into misclassification and wrong predictions. And what are we going to do here? We're going to be, seeing various examples of adversarial attacks and how this works. Geometric perturbations, noise-based perturbations, attacks on natural language models, audio processing, and various others. But more technically, we'll be looking at how do you actually perform these attacks, which typically are performed based on some kind of optimization, typically gradient-based optimizations. We'll study how to defend the networks from being susceptible to these attacks. And, as we're discussing this, as we're showing these techniques, also highlight this trade-off between accuracy and robustness of the network. There seems to be a fundamental trade-off here that we'll keep mentioning at various places. Now, experimental robustness, taking a neural network and trying to break it by perturbing the input, tricking it into misclassification, experimentally showing that this cannot be done after many, many attacks is a good thing. But one question that will be interested in the course is whether we can actually mathematically prove that such attacks are actually not possible. That it's impossible to fool the neural network, the deep neural network, into misclassification. So how can you do this? All right, this is going to be one part that we're going to be looking at in detail, and there is much interest in this space as well from both academia and in industry as well. So let me give you a little bit of an idea about how mathematical certification works, that attacks on a neural network or a deep neural model are actually not possible. So the network is in a sense safe, okay, and cannot be attacked. So let's look at the highlight here again. Let's give an intuition how certification works, mathematical certification works. All right. So over here, on top, we have the concrete reasoning. And here we have some images. Okay, so here we have some images over here. And here I have a bunch of images of the, this is the MNIST data set, for those of you who know, but if you don't know, don't worry. Here's a bunch of images of the digit 7 with different brightening intensities in the image. And there are many more here. I'm just showing you a few of those, okay? And so what happens in the normal operation of the neural network, if you take this 7, let's say you take this one here, the top one, and then we, push it through the network, so this is the first layer in the network, this is the second layer in the network, this is the third layer in the network. So this arrows here represent neural network layers, and the output of the arrow here of the layer are the values that the activations take after this layer. So here, for the first digit 7, over here are the outputs of the first layer. So this would be like the output of the first activation in the first layer. This is the output of the second activation in the first layer, and so on and so forth. Okay, so we can push it through. Here would be what happens after this layer here. All right, so here's the output. So this is all for the first image 7. Okay, so here's the output of the activations after the last layer, let's say. Okay. Now, if we take another image, or let's change the color, and maybe let's just pick another color, some kind of pink color, and let's look at the second image. So in the second image, if you push it for the first layer, it will get different kind of activations, different values for the activations here. If you push it for the second layer, third layer, and so on and so forth, after some layer, it will have these values for the activation, and then the final output layer may have these values. Okay? And there are many more such, many more images that we can push through. You get the idea. So one thing you can do if you want to certify that the network cannot be fooled, is try all of these possible images that you can produce. So all the possible pixel perturbations, within some intensity. If you're doing brightening or lightening, for instance, or if you're doing geometric perturbations, maybe you'll do slight rotations. But there are, potentially, not potentially, but billions of such perturbations, and it's just not feasible to feed all of these, images for the network. Not practically feasible. So if you, for instance, you take, 784 pixels per image, you would have, just for 2 values of the pixel, you'd have something like, 200 to the 784 combinations here, right? So this is not feasible. So one thing that you can do to solve this problem of trying out, billions and billions or potentially infinite number of images, that's or a very large number or bounded number of images, is to do something like this, which is the way that verification tends to work, and certification, is to do the following: is to realize that, well, let's highlight this again here, just so we know what we're talking about. So you can take all of these points here, all of these possible images, all these perturbations, and you can summarize them. You can summarize this somehow. You have to summarize it into a region, over here in green, this region over here, which is something that captures all of these images and can be represented in the computer, in the computer memory. It can represent this shape over here. And so the question is, can we actually summarize these perturbations to the input in some region and to work with this summary instead of all of the concrete images, all right? And this is how certification actually works. So let's see. So instead of enumeration, like this, what we do is we actually work, if you want to think about it intuitively, with a symbolic image. So rather than a single image, single concrete image, like over here, this is a single concrete image over here. Now we work with a symbolic image, like over here, which can potentially capture an infinite or a very, very large number of concrete images over here inside it. To work like this. So how does certification work, really? So what happens is, conceptually, conceptually simple, but technically it can be quite involved. So what you do is you take this green image over here on the left, and you push it for the first layer. You push it for this layer, and once you push it for this layer, once you push it over here for this first layer, maybe that's an affine layer of some kind, or maybe it's a a Review layer or a sigmoid layer or some other layer. And once that happens, you end up with some shapes over here. So we end up with these three blue shapes over here. What are the shapes here? Let's look at what are the shapes over here. These are some convex shapes here. And the way you can think of them is that they're capturing all of the possible, neural activations that can happen after this layer. So these are all of the possible here, that can happen, and potentially some additional ones as well that couldn't exist because of approximation. But let's not worry about this now. So this green images, these blue shapes here are capturing many, potentially infinite number of activations that can happen here. And this pushing of these symbolic shapes continues for the layers. Here you get another shape over here that we're highlighting, some additional shapes. And finally, you may get these shapes over here, which are capturing, you can think of it this way, they're capturing all of the possible outputs that the network can produce for any of the possible images that can exist in the green region. But the way that this works is that we never actually look at the concrete images inside the green region here and run them through. We actually push the symbolic regions for the network in some way. So what that means is that what you need to do is you need to define the effect of these arrows over here, which are now not just propagating a single concrete image, but a single symbolic image. Define the effect of the different layers, not just on a single point, but on a symbolic region, if you like. And that's what how mathematical certification works at a very high level. And the difference between the different methods really is in what the green shape is, what kind of shapes it can represent, what kind of shapes can happen here after the different layers, okay? And also how good your, how good this computation here is, how fast it is, how precise it is, and so on and so forth. And there are many, many different kinds. But ultimately, what all of them do is that they are propagating this, this symbolic image through the network layer by layer manner and produce some output shape over here at the end, which captures all of the possible concrete points that can happen in the green space. Okay, so this is a high-level idea of how mathematical certification works. It's very interesting. It's technically deep, and it's practically desirable as well. All right, let's continue. As I mentioned already, if you want to prove properties of deep models, for example, that you cannot perturb an image in any way, shape, or form, within some range, of course, so that the network misclassifies the points. That's an example property. Robustness, another property. And so verification of properties, any kind of mathematical certification is highly non-trivial and requires a very carefully designed approximations, and something that we're going to be looking at in the course. And as I mentioned already, these arrows that we had on the previous slide, a key question here is one of scalability versus approximation. I can make the propagation of the symbolic shapes very fast, but then you may be including some spurious points that may never actually be possible. So too much approximation, if I make it too fast, make it too much approximations, it means that you may actually fail to prove properties that actually hold. You may fail to prove robustness because you introduce too much approximation. While too little, if I'm very, very precise with my layers in the neural networks, these blue arrows there, the effect of the blue arrows on the symbolic shapes, it can mean that I can prove everything that holds, but I may actually not scale to very big networks. I may be confined to very small networks. And so what are we going to do here? We're going to be studying many different kinds of convex approximations, the symbolic shapes, and as well as how mixed integer linear solvers are used to verify properties, mathematical verification of properties of deep neural networks, together with combinations between, both approximation-based, convex approximation-based methods, as well as mixed integer linear solvers. And we're going to show how those are used to verify robustness against audio, geometric, and noise-based attacks of the kind that I already showed you. Okay. Now, the problem that we kind of discussed up to now, we have attacks, we have a neural network, we want to attack it, we want to perturb the input so that the input gets misclassified. We may also want to prove properties of the network where you prove that you cannot perturb the input in some way, and no perturbation actually gets misclassified, right? And so one natural question here is, how can you actually, build neural networks, build deep neural nets so that, they are more resistant to attacks, they are provably more resistant to attacks, and they are actually easier to prove properties about, okay? And so one observation here that the community has made over the last few years is that if a neural network is not trained to be properly defended, it's not trained to be not trained against attacks, then it, naturally it can be difficult to prove properties about it, either because the properties actually do not hold, actually you can break the network, by crafting particular inputs, or because you cannot break the network actually, but using symbolic reasoning, using certification, actually leads to too much approximation. So the property may not hold, so you cannot prove it, or the property holds, but your neural network is not amenable to certification. And so, one question here is, how do you actually train the network to be more provable? Can we do this? So that's a question that we're going to be investigating. So let me give you an idea about how that works, and the picture here is pretty much exactly the same as the mathematical certification, all right? So just like before, we are going to be taking an image over here, take a symbolic image over here, and we push it through. We push it through the network, okay, and we get some output, symbolic regions after the first pass. And then what we can do, we can use that information at the end, just like in normal training, we can use this convex shapes that we get here so that we can update the weights. Okay, so there's some weights here associated with these layers. So, these layers. And so, think of it this way, I may get some very big shapes here on the right, over here, very large shapes, okay? And then I may ask myself, how can I update the weights, at the different layers, at these arrows, so that the shapes at the end over here get smaller. Think of it this way intuitively. So I can make, multiple iterations like this, taking this symbolic information into account so that I can train a neural network which produces smaller shapes here, okay? And if the shapes are smaller, there's less approximation over here. That means that I may be able to prove more things about the network, okay? So essentially, you use, combining backpropagation, training, standard training with the symbolic information that we have computed, that we compute in the network. Notice how here, you can already see that it is not just a one-time pass. You do the first pass here, first pass for the network. Here we do a first pass. Let's just do it here. We do a first pass. One pass for the network. We get over here. We update the weights, and then we do another pass for the network. Okay, we do another pass for the network. And so these passes for the network, the exercising of these blue arrows here, because they're working on symbolic images. If they're working on these symbolic images, producing these symbolic shapes here and the different layers, ideally this shouldn't be too slow, because if it is too slow, then your training may take forever, because you're making multiple forward passes in the network. And so you want to make sure that's where you also want to make sure it's not just scalability for the verification, it's scalability for the training as well of the propagation of the convex shapes. Right. So this is one point to keep in mind. Now, this also requires a new loss function. How do we actually incorporate this symbolic information into training? And so what happens to the standard loss, cross entropy loss, for instance? Okay. There are many technical parts, to make this, if you want to think of it, symbolic training work, taking symbolic information into account, these mathematical shapes that you get. So for instance, one trick that people have found working well is annealing. Let me just pick a different color here. Over here, let's say pick blue here. Well, not blue because we have blue over there, but let's pick red here. So annealing would mean that we start with the symbolic image on our left, but over here, instead of starting with the whole symbolic image, we can start with some other region over here. Okay, we can start with the smaller region, we can train with it, and then we can consider a bigger region, over here, like this. So annealing, we start with a small shape and we gradually grow the shape, growing it outwards like this. Why does this do? It reduces the amount of approximation error that gets induced, and you turn out that you can get better weights over here at the different layers. Okay. So that gives you a little bit of an idea of how at a very high level how provable defenses work, but there are many questions that remain to be answered to actually make them work. And we are actively working on this topic. Many other groups are actively working on this topic. This year we actually had a paper in ICLR. It's a machine learning conference, an oral paper on a new method to do provable training with deep learning with neural nets. So let's continue here. Okay, there are a bunch of fundamental questions if you want to do provable training. The problem is that, as I mentioned already, there is this fundamental tension between probability and accuracy. And current defenses, as good as they are, even state of the art, incorporating this symbolic information into training improve probability. They make the probability better, but actually negatively affect accuracy. So what that means is that you can think of it kind of intuitively. You can prove more things about a set of images, if you like, but more images get misclassified. More of the data set may actually get misclassified. And so that's again this question between accuracy and robustness, accuracy versus experimental robustness, accuracy versus provable robustness, something that we're going to be looking at. So there's many problems here. For example, can you actually train a model that is both accurate and provable? Can you actually prove that it is always possible to find such a network? Does it exist? That relates to the universal approximation theorem, but this time we are also adding the constraint of probability. What is the connection between many different potentially infinite number of convex approximations that you can use with the accuracy versus probability? Maybe certain convex approximations allow you to get good accuracy and probability, but if it's too loose, the convex approximation that use these symbolic shapes, then actually this may be impossible. Okay, so these are the kind of questions that are both practical questions. How do you actually get a network? How do you obtain a network that is more probable and with good accuracy? And more theoretical question on these connections between the different approximations, accuracy, and probability. And then many more questions. These are just some of these. So just jumping to the course project here. The course project will be about certification of neural networks. It's a very interesting project, based on the feedback last year. The project, will be advertised. We'll advertise the project at the end of October once we have covered the necessary background on, mathematical certification, adversarial attacks, a little bit about training, adversarial training, and so on. We'll have a lecture, 45-minute lecture introducing the project that you can watch. and also ask questions of the TAs. The project will be done in Python in groups of 2, and it will be automatically graded, and there will be 2 TAs, 2 teaching assistants that will be involved with the project. So they will be only focusing on the project. So in fact, last year's project, there was the project was such that was actually publishable. It actually appeared in a conference, a machine learning conference. So it's not super complicated, but it's of that level. It's quite interesting, I would say, and it allows you to kind of apply many of the concepts that we teach in the course in a practical setting. Okay, so just so that you're not under the impression that we're only going to be exploring topics on attacks and defenses and robustness and probability, we'll also be exploring this connection between learning, data-driven learning and logic, as well as the connection between differential privacy and statistical mathematical guarantees on robustness and other properties. Okay, so let me give you an example on this idea of combining logic and learning. Okay, now as these neural networks are making more and more decisions, even bank credit, whether get a credit from the bank, job applications, and so on. It becomes quite critical to make sure how this, to understand how these decisions can be influenced and understood. So let me give you one example of how this happens. So let's use a marker here. 1 second. So here on our left, we have a neural network. We are given a neural network which is already trained. So all the weights are already there. The neural network exists. And here we have an unhappy customer. The customer of the bank was rejected for credit by the neural network. And so one question, that we may ask, the applicant may have the right to ask is, what should I change? What should I change, in my profile? What should I do constructively so that I'm approved for a bank credit? And an engine that combines, logic and deep learning, this one here, some magical engine that exists, can give you the following answer. It can say, look, if you want to be in the 84 probability range of receiving a credit, more than 84 probability chance that you receive the credit, what you should do, you should actually increase your income by at least 5K. So, change your income here, maybe find another job, work harder, get your income a bit higher, and you need to be employed for a few more months, and then you actually be, you have a very good chance for being approved for a credit. So it can give you a constructive suggestion what you can do if you have such a system. Okay. What can happen is that if you do this, you make these changes, you actually get approved for a loan. Let's see another example here. Realize that adversarial examples are in fact just a special case of what we're going to show here. They're really just a special case of a query. Okay, so let's see how they would be seen as a query to the neural network. So over here we have again a neural network which is trained, and we have an input image. And it's hard to see, not so easy. This is from the CFAR10 dataset. That's a deer here. Okay, you can see it. Here's the horns. Okay, and we can pose a query to the neural network. Okay, and here what the query says is, I want you to find an input over here with these dimensions. And this says that every pixel is in the range 0 to 55. Where the neural network classifies the image, classifies the image I that I have to find. I have to find that image as 9, and 9 is a truck. 9 is a truck. It's not a deer. It's a truck. Where there is some don't worry about this notation. There is some amount of perturbation that is allowed, that you are allowed to make to the image. So the O infinity norm here between the distance between the image that we are finding and the original input deer is bounded. It's less than 25 and greater than 5. Okay, so there's some perturbation to the image. So you can think of this here as an adversarial query. I'm asking the neural network to find an input, I, given another input deer over here as input. Okay, and so what the network can do is it can find you such an image, over here. It maybe adds a little bit of noise, and now this is classified as 9, as a truck. So adversarial examples are really, you can think of them as, a very restricted type of query. You can pose many other queries to the network. And if you want to be able to pose such kind of queries to the network, you need to be able to, integrate logical reasoning somehow, or logic into the network reasoning. Okay, let's see one more last example of comparing networks. Okay, so this is another query this time, so a third query where we are comparing networks. So far we only had one network, now we can have two networks. So here we have network 1, here we have network 2, and here we have a query. And what this query has is, so we have 3 inputs, input 1 here, 2 networks, and the third input, which is the image 9. So one thing we can ask the network is to find an input that separates the 2 networks. So let's look at it. So again, we're trying to find an image I. We're just trying to find some image where the pixels in the image lie in some range here. Well, that's the MNIST data set. That's why they lie in this range, where part of the pixels stay the same over here, but some part is allowed to change here. Okay, so some parts stay the same, and this 9 is the input image part can change. And what we want is that one network classifies the image as 8, and another network classifies the image as 9. Okay, so neural network 1 classifies it as 8, and neural network 2, classifies it as 9. Okay, all right. And so if you pose such a query, it may actually, output you such a point over here. Now you get this point from the engine. And this network, this image would be classified as 8 by one network and 9 by another network. Okay, and so here is another example of a query that this time involves multiple networks. Okay, so we saw several examples of queries and why it is desirable to kind of combine, logical queries, something that we want to ask, and deep neural nets. A natural question here is, whether you can actually whether you can actually not just query the network, but whether you can actually enforce some beliefs into the network, some background knowledge into the network. Okay, so that's something that we're going to be looking at. So this is just the comment here on this slide that adversarial examples are just a particular kind of query, and we need to figure out how to combine these constraints to the neural reasoning. So as I mentioned, this question is a very interesting question on not just how I can query a network, but how can I actually, enforce some beliefs into the model, into the network. So let's see how, at a very, very high level, how that scheme would look like. So I have a network topology here. This time the weights, the weights are not trained. The weights are not trained. There's no weights. The weights are not trained. I just have the network architecture. And I have some data set. I might have some data set of images. I can normally train the network, but here I have, one new part here. I have one new thing here, which is this phi, some belief that I have, property phi that I believe in. And I can have this engine over here, which can take into account this phi, some belief. Okay, we'll see examples of such beliefs in the, for instance, in the set of images and other data sets. And after the training is done, you get some weights I here of the network, which is the neural network, such that the network actually satisfies the properties. This symbol here means satisfies this property phi. Of course, it's a little bit more involved than that. It may satisfy to certain probability and so on, but this is the high-level picture. And here's one side effect of being able to incorporate beliefs, background knowledge into the training, into the network. It's that what can actually happen is, this can actually help you increase accuracy, because if you do not have enough label data, you may actually, one way to express belief is, you label the data. That's one way to express belief, but there is many other ways to express belief. One is for these logical, properties. And if you can provide this, even a little bit, it can actually reduce the need for labeling data because you're providing something external. And so what can actually happen is we can specify properties. The various papers exploring this, we have explored this point. Different papers have explored it. You can actually specify properties on the data, on the remaining unlabeled data. And so if you express such properties, you may actually gain enough benefit that you actually do not need to label the data, and you still get pretty good accuracy. So ability to incorporate background information just to pop up and logical beliefs allows you to reduce the amount of training data you need, label data that you need, which is a major problem with deep learning systems. Major practical question that this may solve partially at least. So the question, of course, remains: how do you do this? How do you incorporate logic and background knowledge and all of this beliefs into the network? That's something we're going to be looking at in the course. Okay, so some questions that we're going to be investigating is: how do we actually reconcile logic with differentiable gradient-based optimization? What are the resulting guarantees that the resulting program, the resulting model provides? What kind of properties can we enforce? What kind of specification? How is this enforcement actually done? Here's another question which that's going to pop up a lot throughout the course, and you can make a note of this. How are counterexample inputs over here to the property found? This property, in the case of robustness, was just that the property is robustness of adversarial examples, but then many other interesting properties. And in all of this, you essentially have to find the violating input to the property, so-called counterexamples. But here the space of is quite a bit richer because of the logical constraints that are involved. And there is this question that comes up here often. Pops up in all of the places is the question of projection. Finding the nearest point on the surface of a region. This projection question is going to pop up, and the complexity, how quickly you can do this. There's a very nice question here about the connection between optimization, the particular optimization method that's used, and the logical fragment of the properties that you're using. Okay, this formula phi that we saw, what kind of fragments are you actually allowing there? So very deep questions, very interesting questions that we're going to be investigating in the course, mentioning, and many of them are still not answered. In fact, in the research space, we're only now getting started to more deeply understand this connection between logic and enforcing logical properties and into the models. In addition to background knowledge incorporation, acquiring neural networks, adversarial attacks, defenses, provable defense, mathematical certification, we're also going to take a look at experimentally understanding how networks make decisions. So in the logical examples that we just saw, into the background knowledge, incorporating logic, queries, training, we actually did not care internally how the decision was taken, which neurons actually fired. Now with this direction here, we're actually going to be investigating. We're going to be looking at the neurons that are the groups of neurons that are actually responsible for making a particular classification. And in fact, there is a nice connection between the two, where you can potentially incorporate background priors also on the activations that happen in the network, not just on the input or on the output of the model. So here specifically, we're going to be looking at this still line of work from Brain and DeepMind. Okay, so far we had a very high level, technical preview of the material. Really, very little technical stuff. Just mentioning the directions and why we're looking at them. Next, what I'm going to talk about a little bit is about the course organization, about the course details. What this course is, what it isn't, whether you should take it or not. So really, what does this course aim to do? What is the purpose of the course? the core purpose of the course is to introduce you to some of the latest and most important research in the area of artificial intelligence as it relates to safety and reliability and security of machine learning models. Okay, so very important here, and this is a question that comes up in the first lecture when we are in person, and you can ask me over Zoom, of course, when we have our slot. Is this question, the course really aims to cover core and general concept, logic, projections, optimization, how this mathematical, convex relaxations, various mathematical approximations. So the concepts are quite general, and illustrated with particular examples. And the focus really is both on the general concept and, as I mentioned, with the project, which is 30% of the grade, on applying the concepts, making sure that you can actually build systems that can apply some of these ideas in a project. And last but not least, we want to introduce you to open research problems in the area. This is the problems that that we believe are interesting to look at, and to enable you to actually contribute and formulate different tasks in this space, research tasks. So what is this course not about? Okay, so what the course is not about is the course does not cover, how to design neural networks per se, different neural architectures. We're not going to look at that. There is particular courses for this, for targeting vision or natural language or robotics tasks. Though we're going to be looking at such networks because we need them, to prove properties about or to train them as well, and so on. But there are particular courses that specifically focus on the machine perception, vision, and so on. This is also not a course on gradient-based optimization. We're not going to be studying the Newton's method or first order or second order methods. We're not going to do that. There is a course that specifically targets optimization, constrained optimization, others at ETH. But we're going to be using these algorithms and for some of the tasks that we need to solve. This is also not an introductory course to deep learning or Python. So if you're not familiar with deep learning or Python, you may want to get familiar with this. You definitely want to get familiar with this first. Okay, as I mentioned already, 30% of the grade is going to be from the course project, where we're going to be building a mathematical certification engine of deep learning. Deep neural networks based on particular convex approximations that we're going to be studying in the course. And that should kind of let you apply many of the techniques in a practical setting. 70% of the grade will be based on the final exam. And here I would say you should make sure you do the homework. If you do the homework, I think our experience shows that you do well on the final. All of the information for the course, lectures, exercises, slides, Zoom meetings, everything, project descriptions, everything is going to be uploaded to the following URL. So you just go there and take the stuff that you need. Exercises. Exercises will be in person. Exercise sessions. Come with questions, solutions. Ask the TA. Exercises are not graded, but I repeat this again. If you do them, you have an advantage on the exam. Here is some feedback from that we got from the last 2 editions of the course. The good and the bad here. The course is great. I don't see any major thing that should be changed. The course content is amazing. I really love this course. Course has been different from the other courses I have studied so far. The fact that the course dealt with topics that are pretty recent made it very interesting. I'll generally keep most of it unchanged. The lectures are very interesting. Now let's see how it happens when we're remote. Now, of course, the topics are fun. Pictures of cats are fun, dogs, and so on. But convex approximation is also fun. And, the course has about a 30% failure rate. So I don't mean to discourage you, but I want to make sure that, that there is, the course requires quite a bit of work. And I believe the content is super interesting, new, you learn a lot, but just be prepared to work. So as far as the course, just to pop up, as I mentioned already, this is the 4th installment of the course. 2017 is when the course started. We are constantly improving the course. adding latest material, changing some parts of the course so that it's more and more up to date, so it stays up to date. Here are some improvements that we made in 2020 in this edition. So the course used to be 5 credits in 2019, but we cover quite a bit of material also with the project. Now we made it a 6 credit course to reflect this amount of work. We're adding lectures on, there's going to be additional lectures on fairness, bias, and probability, connection between these topics. And finally, one of the main complaints I would say from last year's course, probably the main complaint, was that the exam was only 90 minutes. Of course, this is scaled in the grade, but this year we decided to make it 120 minutes so that you guys have more time. And as I mentioned, yes, we try to keep RIAI up to date, which can be quite challenging for us. As I mentioned already, one of the goals of RIAI is to enable students to do new research, to discover new ideas in this space, and to push this whole third wave of AI systems forward, to drive this research, to drive the new ideas. And we had many, many students over the last few years. This is just a small sample of them who've come from the course, from master thesis, research in computer science, research in data science, internships, to work with us on the topics that we cover in the course. The course gives you an incredible basis, great basis for doing research in this space after. So there's been many, many interesting topics that students have explored. Spatial transformations, mathematical certification on spatial transformations, audio verification for audio neural network, audio processing, different kind of convex approximations, neural architectures, how to actually construct an architecture, not just the weights, but actual architecture so that it's more suitable for probability, how to transfer proofs between networks. There's theoretical considerations that I mentioned already, this connection between the convex approximation and the provable training, and many other topics that we're exploring. So if you're interested in this space, you want to do research in this space, just send me an email, and then ideally after the course is finished, but generally let me know early. So end of December or earlier if you're interested. Okay, so this was the introductory lecture of RIAI. The goal of the lecture was to just familiarize you with some of the topics that we're going to be covering. Attacks, defenses, experimental defenses, provable defenses, mathematical certification, convex approximation, interaction between convex approximation and gradient-based optimization, background knowledge incorporation of logic into the neural network, the connection between adversarial example and background knowledge, the trade-off between accuracy and robustness, experimental robustness, probable robustness, interpretability, fairness, bias, and so on and so forth. So we'll be covering many of these topics. We also discussed a little bit about the course organization. If you have any questions, you can ask me more tomorrow, or you can ask the TAs. So next lecture is actually when we're going to be starting the technical material. We're going to be focusing on adversarial attacks and experimental defenses. And the techniques that we're going to be looking at here are actually going to be important both for provable defenses and for background knowledge incorporation, background priors. So see you next lecture. Bye for now.